Uh-oh. Am I going? I think. Whoa. All right, let's talk about the exam. All right, let's talk about the exam. I'm gonna show all the data there in a second, but just want to talk to you about something I'm sure you've heard of before, maybe not, but it's called the standard normal distribution or the bell curve. Have you all heard of this before? Basically, the bell curve says, like, if you take a large enough sample of, let's say we're talking about people's heights. Okay, the height of a person. We know that the average human, somewhere between 5 foot to 6 foot, right? So if this is like 5 feet somewhere in here, we should expect a lot of humans to be here, right? And then, of course, we have 6 foot, 7 foot, 8 foot. But there's less people that way, right? And then less people this way. So most distributions, you have everyone clumped together in some average, and then the outside is kind of the exceptions, right? That's what the bell curve means. In a class, when I look at grades, I always hope to see this. Everyone's kind of together, and then you got a few people who really do well on a test. So if this was grades, let's say this is 100 out here, and this is a 0 here, you hope to see everybody together. Now, whether or not this hump is further this way or further this way, I like to see, this shape. Few really good, few really bad, everyone else together, right? It's not the case, all right? In math classes, it's never that. It's always this, okay? Which is basically the upside down bell curve, which is exactly what we have going on with us. If you look at the chart on the left-hand side, this is like A's, B's, C's, D's, and F's. So you can look at like 0 to 100 out here. We have 11 A's on that test, right? 11 A's. We only have 3 B's, only 1 C, and then 4 D's and 5 F's. And that is there were 16 problems on the test. I only graded 14 of them. Number 14 was counted as a bonus, and number 16 was counted as a bonus. And there were some students where I can't give somebody 120 on the first test, right? It's too much. So the highest grade possible was a 110, all right? That was the highest grade possible, and we did have at least one 110, couple, 106, 106, 105, 101. We had students who did over 100, all right? So the class average, okay, the average for the class was a 79.8. Now this is with that curve, right? That's a curve basically, right? Only grading 14 of those problems. So we have a class average of about 80, and then the number underneath that, standard deviation, we talked about what this is, this number? We'll talk about it real quick, 21. That's our standard deviation. So when I'm grading tests, what I'm looking for, what's most important to me is this number right here. This is the one that makes me worried, or it either makes me happy or unhappy. So the way that standard deviation works is this. If you have, let's say, just 2 students in a class, right? Let's say they take a test and you get their grades, and the first student gets a 0 and the second student gets 100. The class average is 50, right? You add them up, you divide by 2, class average is 50. All right, well, compare that to what if the first student got a 25, second student got a 75? Class average is still 50, isn't it? You add them up, divide by 2. Or if they both get 50s, then the class average is still 50. You'll see? So class average, even though it does tell you something, It doesn't tell you or doesn't tell me what I really want to know, which is whether or not the students are together or far apart, right? A measurement of how far apart the grades are from one another. And this standard deviation measures how far apart students are. And a good standard deviation, what makes me happy, is about 12 to 14. When I see anything over like 16 to 17, I have the worst scenario that I ever want, and that is students who get it, students who don't. And so it's hard to teach to that audience. Does that make sense to you? Because I have to challenge the students who are here, but if well, you get the idea, right? So this is a difficult situation that we're in. And it's not surprising, right? This is normal. I see this a lot in math. So for those of you who did well, all right, first test, it's early, don't take your foot off the gas. I hope that things will become more challenging to you. I know they will at some point. And then for those of you who are at the lower end that didn't do as well, you've got to try something different, all right? So we've got to, work at getting tutoring or forming study groups outside of class. Change something, approach the test a different way, approach your studying a different way. Just do something different, all right? And hopefully you'll see a different result the next time. If you do nothing and don't change any of your behaviors in terms of studying for math, then you should expect to see the same result, right? You shouldn't expect to see something different. Questions, comments, concerns, complaints? No? Did you all feel like the test was fair? Would you tell me if you didn't? Did you feel if it was fair or no? Too long? Too short? What? All right? What I did was I opened up the homework assignments and I just started working through them or looking at them, and I just started making a test based on those homework assignments. And then there were some other things that I pulled from class, and then the problems I did in class. So that's how I made the test. All right, anything else before we proceed? It's just the first test, not the end of the world, right? No test corrections, no retakes, right? We talked about that first day. All right. What are we doing today? There were a few problems I wanted to do out of 7.3. Yeah, 7.3. There are a few word problems I wanted to do. Just because we didn't really do a lot of word problems in class. These are directly out of your homework, and I have them, I'm going to project them over here. Let's see, where is it? So I know some of you, it's hard to read this. A blimp is suspended in the air at a height of 600 feet, lies directly over a line from a sports stadium to a planetarium. If the angle of depression from the blimp to the stadium is 32 degrees, and from the blimp to the planetarium is 28 degrees, find the distance between the stadium and the planetarium. And they give you a picture. So I'm gonna draw this picture here. Right? There. So what we have here is a blimp up here. I'll call that B for blimp. And then you have over here the planetarium, P. Then over here you have the stadium, S. And what we're trying to find is the distance between the stadium and the planetarium. So we're trying to find this distance right here. And let's call it, what do you want to call it? They don't call it anything, do they? We'll call it D. That okay with you? Call it D. The only information they've given us is that the distance from here to here, right, is 600 feet. And they've also given us that the angle right here is 28 degrees, and the angle here is 32 degrees. All right, so we're trying to figure out that distance. So who wants to help? How are we going to do this? Go ahead.
I did it, but I have a picture of my notes. Can I look at them?
You can look at it.
I just want to confirm.
What do you got? What's that? Add 32 and 28. And then subtract it from 180. And that would give you that whole angle there? Yes? Do y'all agree with that? We could do that, yes? What are you going to do with that? If you know this whole angle, what are you going to do with that? Could you? If you go here to here, so you're saying let's find that angle, right? And then divide it by 2 to get this? Well, that's assuming that these are the same, but these don't have to be the same. You're on the right track, though. What would the distance, or what would the angle from here to here have to be? What is that? 58. Why? Yeah, because this is 90 degrees right here, right? So that angle right there is 58. And then similarly, couldn't you do the same thing to find this angle right here? Because that's 90. So what would that angle right here to here be? What is it? 62. We can do that, yes? Now what?
Split D into 2 different sections.
Yeah, why don't we just look at this as 2 different right triangles, right? We have one right triangle here. We have a different right triangle here. Let me draw them. Here to here, right? We have this. We have 58 degrees here. And then the other triangle looks like this. Here. And this is 62 degrees, right? And isn't this 600 on this one and 600 right here? Yes? We want to know the total distance from here to here, which should be this distance plus this distance, right? Those two added together should give us the total distance. So I'm going to call this, I can't call this D, right? D's the whole thing. So why don't I call this? Okay, you want to call it D1 and D2? Okay, good. I like that. D1 and D2. So the big thing, and this was on the test, and some of you didn't, I guess, grasp this concept, that is, if you have a right triangle and you have one angle in there and one side, you can solve the whole triangle. All you need is a single angle and a single side, and then you can figure everything else out. Right? So let's see how that works with this one. Here's my angle. This side here, D1, is the opposite side. This is the adjacent, and that's the hypotenuse. Understand? Opposite, adjacent, hypotenuse for this triangle. So what I'm going to do is I'm going to think of a trig function that connects the opposite, adjacent, and that angle together. So what trig function does that? Tangent, right? So I can write tangent of what angle? 58 degrees must equal opposite D1 over 600. There we go. That's my first equation off this triangle. How about this one? Same idea, right? Yeah. We have the angle, we have the opposite, we have the adjacent, and then the hypotenuse. So I can again write tangent, this time not of 58, but tangent of 62 must equal the opposite side, D2, over the adjacent 600. On your exam, I think that what got a lot of people was that this was flipped over. So the thing you were solving for was on the bottom over there, and people had trouble getting that variable. A lot of people got this set up right, but couldn't get the variable right. Okay, questions on that? We're going to keep going, right? Trying to figure out what D1 and D2 are. You have to have this now, right? Because we don't know, right? We don't know what tangent of 58 degrees is. So on my calculator, I make sure I'm in degree mode, right? Make sure I'm in degree mode. I'm going to hit tangent 58 degrees. So this side over here becomes approximately 1.60033, something like that. D1 over 600. How do I solve for D1 now? Multiply both sides by 600, right? That's basically what we're about to do, right? Multiply both sides by 600. So what I want to do is I want to back up to this. I want everyone to understand this is just a number, right? This is a number on our calculator. So you're going to see me start doing this from here on out. If I'm trying to solve for a variable, I'm going to multiply both sides by 600 now. So I'll write it as 600 tangent of 58 degrees equals d1. That's the way I'm going to write it. And then I'm going to go to my calculator, and I'm going to type this all in at one time. I'm going to do 600 times tangent 58. What do you get? 960.2? Good enough, right? 960.2 is D1. All right, so far that's where we are. On this one, same thing. I'm going to multiply both sides by 600. So 600 tangent of 62 degrees is D2. And I type that into my calculator. $1128.4-ish. 1128.4, approximately, D2. And now we just add those two together. So take that answer, add that one. $2088.6-ish. 2088.6, right? What, feet, right? Because this was measured in feet. Feet. Approximately, all right? Approximately. Let's see what it says the answer is. I don't even know if this problem's in mine. Oh, I have different angles, so it doesn't matter. Any questions there? Let's look at the problem on the test that caused a lot of people issues. I just want to look at it real fast. Number 16. I give you this triangle. I say this is H. This is a right triangle. I tell you that's 42 here. And I tell you that the angle from here to here is 105. Right? And I'm asking you to find H. So you're trying to find that hypotenuse of that right triangle. So all you need here, okay, is to know what this angle is. You got to know what that angle is. So we know that all the way from here, all the way over, is how many degrees?
75.
Well, this will be 75, right? Because the whole way is 180, right? So you know that that angle is 75. Once you know that that angle is 75, I have one side of a triangle, and I have an angle, a right triangle, sorry. One side of a right triangle and an angle. So now what I need to do is think of a trig function that connects, which side is this? That's the adjacent side, right, to the hypotenuse. What trig function does that? Cosine, right? Cosine is adjacent over hypotenuse. So I can write cosine of 75 degrees equals adjacent 42 over hypotenuse, which is h. And do you see here how this is different than the last problem? In the last problem, D1 was on the top. Here, h is on the bottom. So you have a couple of options on how to do this. What I would do, okay, the way I look at it, is I first multiply both sides by h. And that gets rid of h on that side. And then I divide both sides by cosine of 75 degrees. Do that over here, divide by cosine 75 degrees. And that gives you h equals 42 is on top, and then divide by the cosine of 75 degrees. And that you can do on your calculator. 45 divided by cosine 75. 42 divided by cosine of 75. 162.3-ish, somewhere around there. H is approximately I said round to 1 decimal place, right? 162.3 is what we're looking for there. Okay? Any questions on this? Yes?
Are you in degree mode or radian mode?
Here?
No, just for getting that last one.
We have to be in degree mode because the angle that we're plugging into the trig function is in degrees.
Okay, is mine giving, really weird. How much?
It depends on how you typed it in. How'd you type it?
I did 42 over cosine 75.
Okay.
And it gave me 42 square root of 6 plus 42
Let me
square root of 2.
Oh, it's not giving, multiply that times 1.0. Yeah, it's giving you some weird exact answer. It does not want to give you a decimal unless you absolutely need it. All right, that's it. We're moving on to the next section. All right? So last class that we were in here learning, not the test, we had defined the 6 trigonometric functions, right? Sine, cosine, tangent, and then all of their reciprocals. When we defined them, I used a right triangle to define them, didn't I? That's when we were establishing what they were, we said, hey, we're going to draw a right triangle. Okay, we're going to call this angle theta. This is going to be the adjacent side. This will be the opposite side. This will be the hypotenuse. And then once we said that, we established all 6 trig functions using the SOHCAHTOA, right? Sine theta is what? Opposite over hypotenuse. I'm not going to write them all down. But the whole idea here is that when I was establishing what sine is, we were using the triangle to understand what it is, right? Sine of this angle is this ratio of this side to this side. Today, what we're going to do is we're going to have a new definition of what sine is. And we're going to base it on a different picture. It's not going to be this picture. And so you might be going, well, why would we need to do that? Like, we're happy, right? Like, let's just stay here. The reason we need to do a change is because right now on a right triangle, this angle is restricted. It can only be between 0 and, for a right triangle, right? The biggest this angle could be is what? 90, and then it wouldn't even be a triangle, right? But so right now, we have only defined the 6 trig functions for acute angles, right? Angles less than 90 degrees, 0 to 90 degrees. We need a definition for the trig functions for all angles, because we've seen when we were looking at angles that angles can go, counterclockwise, clockwise. They can go into each of the 4 quadrants, right? So this is good, but it kind of limits what we can do, right? So here's the new definition. So this right here, this is good for acute angles. Not for angles bigger than 90 degrees. All right? So the name of the next section, 7.4, is called the trigonometric functions of any angle. Of any angle. Not just acute angles, of any angle. So we are now officially moving into 7.4. And you ready? I'm going to give you the definition, all right? Here's the definition. Let's not attach our brains to this anymore, okay? We have to be willing to leave this idea. So the way we're going to do is this. Imagine that you have the XY plane, right? And you can think about an angle, right? You can think about an angle starting out going, standard position means that we always start with a ray that goes from the origin out the x-axis, right? And then we open up the angle wherever we want. I'm going to place an angle somewhere. Let's just do this angle right here. And we can imagine somewhere out here, just some arbitrary point out here. Right? I have established an angle, haven't I? The angle I'm talking about is this angle from here to here. That is called theta, all right? Now, this point that lies in space, right, this point right here, has both an x and a y coordinate, right? This has some x coordinate. In this case, the x coordinate would be negative, wouldn't it? And the y would be positive. So I'm just going to put here, I'm going to label it, that this has both an x and a y coordinate. So far, okay? Also, from our not first day in class, it was after partial fractions. Right after partial fractions, do you remember we talked about how we can find the distance between 2 points? Right? The distance between 2 points? If I give you this point, x, y, and I give you the origin, the point 0, 0, can you find the distance between those two? Yeah, you have a formula for it, right? So if you needed to, you could find that distance, couldn't you? If you needed to? So let's call that distance something. Let's call that distance r. Okay, so r is this distance from here to here. While I've got that up over here, I'm going to give us a specific example next to it so you can kind of see this with real numbers. So as an example, let's say we took the point -2, 4. Right there. That point, -2, 4. There is an angle that is formed right here, right? That angle right there, we call that theta. Can you tell me how long this is? Can you find this distance from here to here? We're going to call it r, right? Let's call it r. But can you actually calculate it for me? How would you do that? There's a couple of ways to do it. Anyone? I heard distance formula. Is that what I heard?
Yes, sir.
You could use distance formula, right? Yes? Another thing you could do would be kind of clever is to think about this as being like a little right triangle. Do you see that little right triangle there? How long is this side? 4. How long is this side? 2. And now can you find that side? Yes, Pythagorean, right? So you could say that if this is r, this would be 4 squared plus 2 squared equals r squared. That's 16 plus 4 equals r squared. That's 20 equals r squared. So what's r? Yeah, you can go cleaner than that. I mean, 2 root 5 is fine. I'm going to leave it as root 20. Okay, so let me get back to what I was saying here. If you give me an angle, I can always get a point on that ray, have the x and y coordinate, whatever that is. Once I know that x and y coordinate, I can determine what r is, right? So if you give me a point, that determines an angle, and I can always find the radius going out, or the radius, we call it r. Does it make sense that that's a radius? Imagine like a circle here. Okay, so that's r is this distance from here to here, and we can find it, right? All right. So now, once we have this, let me tell you what the trig functions are. So using this, by definition, I'm going to even put that here. By definition, when we say by definition, it means this is the way we define it. Sine of this angle, sine of that angle, will always be the y coordinate divided by r. That's the definition of sine of an angle. All you have to do is take this y coordinate, whatever that is, and divide it by this radius. And that's what sine of that angle is. Cosine of the angle is the x divided by r. So you're just going to take the x coordinate and divide it by the radius. And then tangent of theta will be the y coordinate divided by the x coordinate. That is the new definitions for our trig functions. Yes?
I had a question.
Uh-huh.
I was trying to ask about that one.
Yeah,
Do you
go.
always exclude the negative, like when we go to like pull the values out?
Okay, so when I said, I said to y'all, look, we have a point, right? And we have the origin. You could find the distance between this point and the origin using the distance formula, which we talked about a while back, right? Give me 2 points, we have a formula for it. Or you could draw a little triangle and think about the lengths of these sides. How long is this side? 4. How long is this side? 2. With me? And then you can solve r. So there's two. That way, I like this way because you avoid the distance formula. Even though mathematically you're doing the same thing. Like you're actually computing the same thing. It just looks different, and people like that more than the distance formula. Okay, what do you think? Did I answer your question? Okay. What do you think the other 3 trig functions are? Like, what do you think cosecant of theta would be? Is what?
1 over 1.
It's the reciprocal of what sine is, right? And what's sine? Y over r, so cosecant should be r over y. And then what's secant? Well, that's the reciprocal of cosine, right? So it should just be r over x. And then cotangent will be the reciprocal of tangent, so x over y. Yes?
So going back to what she said, whenever you're like, would x equal -2 or +2?
That's a good question. Yeah, very good question. I'm going to answer that. We're about to do this right now. Because I think the question was, well, I don't know what the question was now. I'm a little confused. Were you asking me what x will be, or were you asking me when you calculate r, do you put a -2 here or not?
The question was, should we always disregard the negative? As in, like, if we were to do this on our own, and like it was another distance, like let's say it was -6, we would just do 6.
If you're trying to figure out what r is, it won't matter.
Okay.
It won't, even if you left it negative, it won't matter with Pythagorean, because what does Pythagorean say? This side squared, this side squared. So if it's negative, it's going to get squared and it's going to become +4 anyway. So you can't go wrong by putting it negative. I was just saying it's a distance on a triangle, so normally we don't look at that as negative. Now that doesn't address your question, which was when we do this, are we going to treat that x as negative, or are we going to treat it as positive? I think that was your question, right? So let's do this example right here that we have. Now that we've established, we have the point, right? We have the x, we have the y, and then we said we calculated the r, right? So let's go figure out what sine and cosine and tangent. I'm going to have to do it over here. So for that example over there, what would sine of that angle be? By definition, it's y over r, right? What's y for us here? 4, and what's r? Root 20. We're done, okay? Yes, you could rationalize the denominator. I'm not going to. Cosine theta is the x coordinate. The x coordinate.